not so much about, this is not so much about the components out of which we build models or the uses of the letters of the analogy vocabulary, but rather it has to do with one of the important processes undertaken with respect to dynamic models. Dynamic models of all sorts, of all the three sorts we looked at this morning. So these processes will be talked about. Sensitivity analysis today, calibration tomorrow. How to cross dynamic modeling types, their common meaning. Although the texture associated with them varies a little bit from modeling type to modeling type due to the presence, for example, of stochastics or versus deterministic specific context. In this case, we're going to be diving into the issue of sensitivity analysis and just taking a glimpse at something that could by itself occupy half the course. Sensitivity analyses that are undertaken with respect to dynamic models differ dramatically in their character. Some of the ways in which they differ are indicated up here on this slide. In some cases, it's very commonly conduct sensitivity analysis with respect to parameter assumptions, with respect to the values that we assume for certain model parameters that make specific assumptions about processes in the world. And often those are conducted in a one-way or a multi-way sort of fashion. Is there one parameter at a time or multiple parameters at a time? We can also distinguish between parameter sensitivity analysis of these sorts and structural sensitivity analysis, where we're examining the impact of model structure on the outcome. Here we might do something more fundamentally, such as add a state to a state chart, eliminate a transition, or combine states that existed and see its impact on model findings. These are especially important when trying to resolve incompatibilities with empirical data, for example. In some cases, we provide we run the model with single alternative values of parameters or with different model structures. In other cases, we perform what's called Monte Carlo analysis. So we run the model again and again and again, drawing different realizations of model values over time, different stochastic realizations, in order to assess the broad regularities of model output, put aside the vagaries of one realization or another. So we run the model many times over. And finally, we can capture within our model stochastic processes, and that's the norm for Bayesian-based models. In other cases, we perform sort of static varied assumptions about a particular parameter. So we assume for the entire run that a parameter has a certain alternative value. So in this case, I think I'll skip this slide. Suffice it to say there are some significant issues concerning the choice of models and identifying the appropriate model. With lack of time, I'm going to focus predominantly in this lecture on parameter sensitivity analysis and show how this can be accomplished. In this case, we're going to be varying parameter values and looking for parameters, for how different parameters affect model results. An extension of this would be to look at how they affect the choice between different policies, the trade-off between different interventions. There are certain types of changes in parameter values that might yield significant difference in model results, but do so in a way that doesn't really change the relative desirability of different interventions. Perhaps we have intervention A and intervention B as judged in terms of desirability for any number of different criteria, maybe dollars per quality adjusted likelihood space, and it may be that A looks more favorable than B for our default values of parameter assumptions. And when we change those parameter assumptions, perhaps the two individually change quite a bit, but consistently A still outranks B. That's a common occurrence. And so sometimes we look at not just the impact of changed parameter assumptions on the model itself, the choice between policies. It's suffice it to say that we often will use static sensitivity analyses to then prioritize data collection on different parameters with the goal here of identifying parameters where the assumptions make a big difference, so that we can spend more efforts in terms of estimating them versus those that make small differences. Various ways of presenting it, but here I really want to give you a hands-on approach to conducting sensitivity analysis within this platform. Tools such as spider diagrams could be used to capture and summarize the impact on model output as measured by the distance from here of different assumptions or different parameters that might be varied along the x-axis. In this case, we're going to be looking at a different form of output, which is going to be in what's called a two-dimensional histogram. So we're going to look at how different parameter assumptions modify the model output over time on the x-axis by seeing where it falls in different categories of possible values. And we're going to run the model again and again and again and see the distribution that appears there for a given period of time. And we'll do that for many periods of time here. So conceptually, we're going to have a slice through here where there'll be a histogram created for that slice of time, created by running the model many times over and observing its value at a certain time. Okay, so we're going to see how this is done within this particular modeling software. And to that end, I was hoping that we could open up an example model called SAR agent-based calibration. Now this was one that people had noted before on the very first day when we were trying to find that very first model. There are two with similar names, so you want to watch out for it. And you go with help example models here, and then under the example models, I believe it's one of those, yes, right here on the right. SAR agent-based calibration, okay? So if we open up that model, this is a familiar situation. We have the same basic framework we examined on that very first day, that very first model. And we have people, state charts are depicted as such, arranged within a population. Nothing surprising here, nothing unfamiliar. What I'd like you to double click on is this Monte Carlo TD histogram here. So this is an experiment, but it's a different sort of experiment than we've seen thus far. Thus far, what we've seen is experiments that run the model a single time. They run a single realization of the model. The model is run with a single initial random number seed and plots out some stochastic realization with respect to its variables over time. Here, what we have is an experiment that actually runs the main class many times. And in this particular case, we're going to be running it 200 times with the same set of parameter values initially, okay? We're going to do so because of stochastic variability in the model results, and we want to assess the impact of that variability. So this parameter variation experiment is a standard experiment type within any logic. If we did new experiment, we'd see that there are a wide variety of experiment types. Thus far, we've really confined our attention to a regular simulation. Very useful. We can change parameter assumptions for that simulation. But now we're making use of this parameter variation experiment. Okay, so let's go actually run that. We do that in the standard way by just right-clicking on doing run. And the key point here is we're going to run this model several times over. You'll notice that I've made two of my cores available for use by AnyLogic. It's actually, for whom this is a meaningful statement, it's actually running this model in parallel on separate areas of my computer's processing capability so that they're going on concurrently. In general, it can take advantage of an arbitrary number of cores. I've used it up to 16, so limitation above that. what's happening here in each of these simulations for the model again and again and again, and it's plotting the output of each of those simulations in a quantized sort of manner on the top of the screen here. So if we consider a given square here within this line here, suppose this one just after this times 40. What this is saying is that the fact that we see different intensities, different levels of darkness associated, say, with this square, this square, this square, and this square, it's telling us that different number of realizations, different numbers of particular runs of the model with specific random number of keys led to different counts of intersections with each of these boxes. So the largest number of cases of realizations fell within that box here. So a large number of trajectories jumped through this box, a smaller number here, and a smaller number yet up just below that 2,000. So if we look at a given run of the model between times 40 and times 42, I believe it is, that would have led to incrementing the count in one of these boxes along the XY axis. And this is simply summarizing the number of cases that have fallen into that area. Again, if we cut it at that time, if we were imagining a cut just after time 40, going vertically here, what we see is a histogram. There'll be some number down here by 0, it'll be bimodal. Then it'll be essentially 0 to this point here where it would rise, fall again, and then essentially 0 after that. So here we have a summary of 200 runs of the model, varying no parameters in this case. There's no parameters being varied. Instead, we're just running the model again and again and again, and yet we see that variability. Could you help me understand, folks, if we were to go back to the model, if we were to go look at this person class, whence is this variability coming? From what source do we see this variability? Why do we see this variability in output writ so large on this diagram here? From whence does it arise? Good. So there's in fact several processes. That's great. So we have the recovery process, for example, and this is dictated by the rate. This is mean time people spend in the state. Some people leave earlier, some people leave later. And the vagaries of those stochastics will lead to some variability in that trajectory. Similarly, we have here a message here being sent to a random person in the population, and to whom it's sent may make some material difference. If it's sent to someone who's already infected, they won't be infected again. So we have vagaries associated with this model run, and it's because of that that we see this variability realization to realization. And what's notable is that a given run of this simulation, most of them seem to vary around this point, but you'll notice that there's a non-trivial number that actually still lie down here in the bottom. Many of those, it's important to recognize that you can't read off directly from these graphs the individual trajectories. Some of these trajectories down here at the bottom, some of the reason these are darker may be because a trajectory is going straight across, but in many cases it may be a trajectory that's simply a late bloomer. It only rose up later in the process, or a trajectory that came down early that only had a partial line. So we have to be cautious about reading a diagram like this. It's not tracking particular trajectories, but it does give us a sense of the range of variability. And we see, for example, that very, very few indeed fall into this region. There's a greater chance of falling down here in very few cases or many cases here. So this is an example of sensitivity analysis without varying any parameters within any logic. It's also notable that when we ran the sensitivity analysis, and for those who have just arrived, I would suggest that you do help, example models, and in this default list here, you go down to SAR agent-based calibration, That's the model with which we work. So when we ran this model, and I do so by running this Monte Carlo 2D histogram, the final experiment, that it was running it in a way to display this graph, but it was not displaying that big sort of field of agents. It says 250,000 agents, if I'm not mistaken. So it's that familiar model we saw earlier in terms of the number of agents, but it's actually running it without showing it. And it's significantly faster in this form than it is if it was actually displaying it. So running the parameter variation experiment runs the model in what we call in computer science a headless fashion, meaning it has no output. It has no visualization associated with it. And that can mean a very material speed up in the performance of your simulation. So you run the model here 200 times in a somewhat parallel fashion with the results summarized. No parameters have been varied in this case. We're going to proceed next to examine a situation. So this summarizes purely the results of the vagaries of stochastics in this model. We'll next proceed to examine a case of structured variation of parameter values and see how that affects these trajectories. Before I do that, are there any questions about this? Yes?
What's the y-axis here?
The y-axis represents the number of infected individuals at a given time. So if we consider this case, let's say just after time 40, let's consider the darkest sort of little box. This is what we call a bin. It's a histogram bin. But it's a bin both in the x direction and the y direction. What this is saying is between 40 and I believe it's 42 here, there were a large number of trajectories that achieved between perhaps this, 1,400 and 1,600 people infected at that time. And there were comparatively fewer, say, that had over 2,000. It's very light, and there are almost none below 1,000, except for down here by 0. So the darkness here of a given bin indicates the number of trajectories which for a certain time interval had exhibited a certain range of number of infected people in the model, prevalent case stuff of infected. Does that make sense? Okay. Other questions?
So,
Yes.
so there's no time after.
There is a time. This is time here. The x-axis is time.
So this doesn't mean that after, for example, 80 simulation or repetition, you have no.
No. And I can understand, Ross, why you're confused about this, because by happenstance, there were 200 runs done, and this says 200. But this actually is the finished time of the model. So maybe we'll clarify it to do something like this. I'm sorry? Yeah. I'm going to run it now 500 times. How do I do this? I go down to this parameter variation experiment, and I say number of runs 500. And here I'm going to actually run it 500 times. I've made all 4 cores on my machine available and speed it up. But here, again, each is being run 2 times 200. How do I know that? If you go here and you look at this and you scroll down, you'll find that model time, the stop time, is 200. And so each of these runs is run at the time 200. And this x-axis is giving time. So at a certain time. So in this case, this first box after time 40 is between time 40 and 42, I believe. And what this is saying is that that for that time 40 to 42, there's a large number of different realizations which exhibited between 1,400 and 1,600 infected individuals at that time. Does that make sense? And it's running it 500 times over, and from seeing it 500 times over, we get some sense of the variability exhibited from realization to realization. We'll see how many times exhibits a very, very diverse values. And you can see there are a significant number that remain down here that are down here at 0, right? So there it is. It's somewhat more, it's a little bit more textured perhaps than was green, although it's not bad. This is good for vector, compared to semi-four, of course. Okay, so this is with no variability in parameters. Purely stochastics caused by the vagaries of when people recover, to whom they send the messages, that sort of thing. So any questions on that? Okay, so let's take that same same situation, and let's go, and we're going to vary the particular parameters. So within experiments, as we've seen before, within experiments we can vary parameter values. Okay, so I'd like you to select this experiment, and I'd like you to go now and up to this area that says parameters. We've used parameters, experiments in this form before to vary our parameter assumptions, but now we're going to do it in a systematic way as we vary those parameters. So specifically, we need to select varied in range, okay? When we do this, we should be able to specify several different values here. Okay, now so why is it I am not seeing that interface here? Okay, so there we go. I just didn't click it properly. Okay, so here we have several different parameters: average illness duration, contact rate, infection probability, total population. What are these things? Why are they listed here? Because they are parameters. They're parameters in main, specifically. So if we go up here and we list parameters, these are the parameters in main. Okay, so we can, for example, ask to examine average illness duration, and I'd like to vary it from 5 to 25, step 5, okay? So here we go, it's a range, 5 to 25, step 5. So that means we'll, in successive runs, we'll be examining successfully larger values associated with this parameter. You'll note that there are specifically 5 possible values for that parameter. Okay, I would like to run that, and you should see something along these lines. So if we run it out, we'll see something like this. Can anyone interpret what's going on there? Anyone want to hazard a guess? Well, these will summarize the model's trajectories for 5 different runs of the model. One with value 5, one with value 10, 15, 20, 25. Making successively larger assumptions regarding the contact rate, how frequently a perceptor will come into contact with other people, will lead to successively sort of more pronounced and longer lived. That's their average illness rate, how long they stay with infection. So it leads to longer lived infection. Now this is only running one time per realization, or excuse me, one time per alternative assumption, or what we call an iteration. We can use replications here, in which case we can basically tell it, for each of those, I'd like you to run it, say, 10 times. So for each of those five different assumptions concerning average illness duration, I'd like to run it 5 times, and that will capture some variability around those points. So here we've run it 5 times for small average illness duration, so 5, 10, 15, 20, and 25, and there's some variability associated with a given assumption. So how did I do that? The first thing I did, just to vary the parameter, was up here in the Monte Carlo 2D histogram. I set these things to vary in range, set the range to go from 5 to 25, step 5. Second of all, I scrolled down and I said to use replications, and I said a fixed number, and I said 10. So in that case,
for each of these parameter assumptions for average illness duration, we'll run it 10 times over to capture the effective variability associated with stochastics. So this is for a single parameter. Any questions about this? Any questions? Okay. So I'd like to turn off replications here just to sort of simplify our reasoning for the next step. I'm now going to perform a multi-way sensitivity analysis. So here we're going to change several values together. And the reflection here is that there may be some interaction terms between, some interactions that are going on between different parameter values. For example, average illness duration may combine to interact with some of these other assumptions to yield behavior that's distinctive. So in this case, I'd like to specify infection probability as going from 0 to 1 with a step of 0.1. So infection probability, we're going to set it to vary in a range from 0 to 1 with step 0.1. Okay? Okay. And let me make sure what it's, yeah. Its default value is 0.8. Okay, so here we're going to perform a multi-way sensitivity analysis. You'll note that there's 11 possible values, 0 through 0 through 1.0. Okay, so there's 11 possible values. Okay, so now let's run that out. We've turned off replication, so we're just running it one time for each combination. And it's running various functions.
Unfortunately, this is where the projector breaks down a little bit. There's actually some runs further out in on the right-hand side. Maybe some of you have seen them. You'll notice it says 55 runs here. Where did that come from? From whence did that come? 55. 5 values of 1, 11 together. So the 5 values of average illness duration, 11 values of infection probability, different contexts, and hence the 55 is just the result of all the Cartesian products of all possible values. We examine one with the lowest possible value for infection duration, lowest possible value for infection probability, another with the next highest value up for infection duration, the lowest possible value for infection probability, and so on.
Okay. So we have ways of easily performing multi-way sensitivity analyses as well. One of the challenges that comes about by this is that if you want to conduct sensitivity analysis with respect to n parameters, there's going to be a combinatorial explosion in the number of different values you have to look at, different possible parameter combinations. Without going into it now, there's ways through dimensional analysis techniques and techniques for judiciously selecting combinations, such as orthogonal arrays or Latin hypercubes. There's ways that can be used with any logic with a modicum of mechanisms to allow you to reduce the number of parameters that you have to vary simultaneously, and to reduce the number, most importantly, the number of combinations that you have to retain. I'm going to talk a little bit about the use of Monte Carlo techniques here as a way of sampling space in a less explosive fashion. We won't talk about that. Okay, Latin hypercubes, orthogonal arrays. You'll find me talking on the web about those things. Right. So here we're going to feed in for Monte Carlo analysis. Let me see if we're going to feed in probability distributions to reflect our uncertainty about one or more parameters, and we'll run the model many times for different parameter variations. And we're going to see a probability distribution emerging from model outputs that is reflective of both stochastics and of variation in parameter values. Don't think I'll go into this here, but we're going to go through and we're going to impose parameter distributions for particular model parameters. So what I'd like you to do is to go and set these back to fixed, and we're going to instead impose a distribution for them. So for average ultimate duration, perhaps we'll impose a distribution as given by this formula. We'll draw a value. It'll be a truncated normal distribution with a normal associated with a standard deviation of 5 and a mean of 15. And forgive the affront of reversing those two. So here we're going to run the value a specified number of times, and here we're going to do it. Ooh, excuse me. Okay, hey, come on. So we want to do it 200 times. Okay, I'm sorry. I'm doing this the wrong way. I just realized we should actually be doing free form here. We shouldn't be doing this in varied and range. Sorry about that, folks. This should let me go set that back to its original value. We should be doing it in this free form way instead. So free form, and that's what allows us to specify this number of counts. So this is what we want. I was doing it before in this sort of way, putting it here. That's not what we want, although it might work. The one I know works is this free form sort of way. We can put a value in here. Oh, it seems to be exhibiting a certain truculence for accepting this value. So here. Sorry. What am I doing? Okay, this says free. I think it's. Oh, that's interesting. Okay. So we want freeform. I think it's not. Yeah, I think something like that's going on. Okay. So we want freeform in this. I think you're right. That looks to me like a bug. It's happened twice now. Okay. Several times. Okay, thank you very much, Gil. Much appreciated. So freeform, number of runs 100, and for each it's going to draw this value from this truncated distribution. It's going to draw from normal distribution, and then we want it to be a minimum of 0. We don't want it to go below 0. Okay, so I'm going to run this model now, and here we're drawing this parameter from this distribution, which may be based on some empirical data with variability in the population, a certain level, or what have you. And we want to see how that sort of variability empirically might make a difference. So this is the result of feeding in a distribution, as it were, for a given parameter value, and it's also combined with the model stochastic to yield histogram output. Now, this sort of seeing it here visually is gives us some benefit interactively, but to really analyze this seriously, you want to export it. You want to export it to either a package like R or a statistics package. You want to export it to at least some form that you can process it in a package like Excel. So I'm just going to call up Excel here to show you how that can be done. So if you go to into Excel or a similar type of package, you can then paste. How did I do that? I just went here. I did copy all. I right-clicked on this, did copy all. Called this up, and I pasted. And what this is giving is the 2D histogram bin count. You'll notice that this is saying between times 0 and 2.5, all 100 of the simulations, all 100 realizations that I ran fell within from 0 to 200 infected people. By contrast, if we look at time 20 to 22.5, 20 of them were 0. There were one at 2,000, another one at 2,200, but the largest number were up here. It looks like the mode of it was 5,800 to 6,000. So this is the basic data that's underlying this graph, and that's being displayed there. And in the past, we've exported this sort of data to R to create the 2D histograms in R of it that are more aesthetically acceptable.
How would you get export, because that's already summarized overall simulation.
Mm-hmm.
How would you just export all the data about the simulation and apply the final data at the time?
Mm-hmm.
It's not that hard to export all the data about
Right.
simulation.
That's a good point.
Seems like that's what you really want to do if you really want to get some sort of statistical
Sure.
information.
Sure, you can do this. This is binning it in a regular bin grid. But as far as exporting, so let me think about the best way to do this. There's certainly different ways to do it.
In some cases, you don't even really.
You'd still be sampling it over time, presumably. You know, at certain fixed points, you'd be recording it. Okay, that's a very straightforward thing to do. What you would do is remember that each of these 100 simulations is occurring over time, and it's occurring in a particular instance of this main class, right? So let's go see how we can do that. I admire the question. So suppose I wanted to keep track of this. In fact, it's already shown how we do that. So I don't even have to create it myself. In this case, what's happening is that we're accumulating here every 2 time units. We're accumulating the number of infectious people in a given simulation. And this experiment is running the main class many, many times. And each time it runs, it actually extracts the data from that run and adds it to its 2D data set, this binning data set that's summarized here. And so we could instead, rather than adding it to this data set, we could write it to a file instead. And that could be done by writing out this data set here. Should be, I'm trying to remember even if there's a built-in method for, yeah. That's right. That's right. I think, trying to remember if there's it may be that you can actually just essentially print this out to a data set by using the appropriate. I think it may get printed out as a comma separated thing, and you can put it to a appropriate file. I'd be glad to explore that later, but I do want to get through this. So, yeah, this would be the point to do it. So after the simulation run has been made, after you've run main once, you can dump that out to a file. Yes, Kurt? Oh. Okay, it may have run out of batteries, or is it working again? It looks like the battery's been exhausted. It looks like the battery is not exhausted. Looks like the button got pushed. Thanks. Yeah, so this could be written to a file at this point. And we can do that, I'm trying to remember with confidence. I have, there's a couple lines of code you can use to write it to a file quite trivially. I think it's essentially as if you're printing out a string, but you print out the data set. Just goes to that file. The biggest thing is opening up the file and then closing it at the end or something like that. In this case, you'd append it to the file, and each of them would just be rows in the file. Yeah. Another thing that you could do, and I discussed this with one of the teams before, is AnyLogic, and I've been known to give lectures on these subjects, but AnyLogic also offers connectivity to Excel files and databases. And so one thing you can do here is, for example, into main, if we opened main here, we could go to the palette and we could drag in a text file, and this would be output realization output or something like that, right? And we could tell it, okay, use the comma separator, right? And this would be a write, telling it to write to it. Oh yes, write a 10, thank you. And we could go put it on the appropriate place. So realizations, UCLA realizations or something like that. And then when we're at that place here, we could essentially write via that file representation we created. Okay, realization, output, output. Realization, output. Oh, of course. This doesn't live here. Where does this live? Where should this live? Oh man, I shouldn't have made that rookie mistake. Where should that live? Does it live in Maine? What's longer lived than Maine? What outlives Maine? Well, that's a true point. But I don't want to embed a realization output in you. So what outlives Maine is the experiment. The experiment runs Maine many times. It creates Maine, it runs Maine, and Maine disappears, and the experiment still runs. So the experiment is bringing mains into existence, running them, and reading data from them and destroying them. So it's actually in the experiment that we want to do that, and we would do realization output dot, and I think it's basically print. I think we could basically print that. So print of this data set, if I'm not mistaken. I believe that should work. But I'll have to double check that later. Okay. In any event. Okay. So I'll leave that there for. Okay. So this is running the model many times. As I said, this will make a very significant savings in terms of runtime. So sometimes when you want to run your model quickly in the first place, you could just create a parameter variation experiment, not because you're interested in watching results from it, but you simply want to run your model without visualization. And that can save a lot of time for certain models. It means it doesn't have to do all the work of showing it on the screen. So once you're confident your model is working fairly well, if you just want to output some data from it, you can create a parameter variation. Run it one or more realizations and output data accordingly. Okay? Any questions about that? Sensitivity analysis. Yes. Great question. Yeah. So within this context, in fact, within all experiments, we have an issue that when we rerun it, we need to determine. So within these runs, there's a sequence of random numbers that are used. Figure out, for example, to whom a person sends messages, when they'll recover, etc. And there's a thing called the random number seed that basically dictates the particular sequence that's going to be occurring over time. It dictates, taken together with the model, it dictates that. And for a given experiment, and this is true for a parameter variation, but it's also true for other types of experiments, we can either say we want to take a random seed
that's chosen. Typically, I think it's based on the current time in milliseconds, time since 1970 in milliseconds, which is the date 1970. Alternatively, we specify fixed speed. If every time we run this model, we want to see exactly the same thing, precisely the same thing. If we don't modify the model, we'll see the same thing as we assume that fixed speed. Okay, assuming we're not changing something else some other way. You can also set it to use some sort of custom mechanism for generating this. But yes, you can specify for a given run, like if we see a run which exhibits certain interesting behavior, we might want to fix the speed on it so every time we'll see that behavior and we can investigate it. In fact, we used that last night for debugging that problem. So you can set a fixed speed or you can use a random speed. The random number generator components of this are fairly standard. They're using Java random number generator mechanism, and you can use those custom ones if you want. Is that helpful? Okay, any other questions? Okay. I think that's good. About to a plot. My thought would be I could give another lecture certainly. I could give a case study, give a lecture, but my thought is to use this time for projects. People like that? Okay. Thumbs up. Okay, so we'll take a brief break and we'll get going on the project. I have a confession to make to the group. And the confession is I'm really bad with names, and I'm also not that great with faces. And what's that? And what this means is that myself and truth be told, even our PA, have been talking about the different groups as, oh, it's the group that sits towards the front, or it's the one that sits at the back, or the one on the right-hand side, or whatever. And if you reorganize yourself, we're going to have a double of the time.
Yeah, don't do that.
It'll be like blind man's bluff. It'll be like, so you're talking about prenatal issues, and it's actually about, dentistry clinics or something. And so if you could set it roughly the same configuration as yesterday, that would be quite helpful. For sort of, if only because we're referring among each other, we say, oh yeah, the group in the front is working on this model, and now if you switch to the back, we'll be all confused. There was at the front, and now it's at the back. So please try to fit in the same place. But it would be helpful if they... I don't know what sort of comment that is, but anyway, okay, so we'll start up with projects presently. Thank you.